Introduction to the four-step travel demand model. The four-step model is a macroscopic, sequential framework used in transportation planning to forecast future travel patterns. It operates at an aggregate level, using traffic analysis zones, TAZs, as its fundamental geographic units, and representing the transportation system as a link node network, macroscopic versus other models. It is less detailed than activity-based models, which simulate individual traveler behavior, and microscopic simulations, which simulate individual vehicle movements. Sequential nature. The output of each step becomes a primary input for the next, creating a logical flow from overall travel demand to specific network routes. The model answers four key questions. 1. Trip generation. How many trips are produced and attracted in each zone? 2. Trip distribution. Where do these trips go? From which origin to which destination? 3. Mode choice. What mode of transport is used for these trips? 4. Route choice, assignment. Which specific route is taken on the network? Phase 0. Prerequisites and setup. Before the four steps can begin, critical foundational work must be completed. Point 1. Study area and zoning. TAZ definition. Study boundary. The geographic scope, e.g., a city or region, is defined, including external stations to account for trips entering or leaving the area. Traffic analysis zones, TAZs. The study area is divided into smaller, non-overlapping TAZs. O criteria. Zones are created based on land use homogeneity, population and activity density, and road network continuity. O size. Zones must be small enough to reflect land use variations, but large enough for practical data collection. O centroids and connectors. Each TAZ is represented by a centroid, a point representing its travel origin, the destination. Centroids are connected to the actual transportation network via connectors. Point 2. Transportation network creation. The network is built from nodes, points, e.g., intersections, interchanges, and links, the roads or transit lines between nodes. Link attributes. Each link has defined characteristics like length, speed, capacity, free flow travel time, and cost. Multimodal networks. Separate or integrated networks are defined for different modes, e.g., private car, bus, rail. Point 3. Data collection for model estimation and validation. 4. Calibration and validation. Startled smiley. Calibration adjusts model parameters to match real-world conditions. O validation checks the accuracy of the model's forecasts. O data sources. Household travel surveys, origin destination, OD, surveys, traffic counts, passenger counts, and travel time. Is speed data from GPS or sensors. For model estimation. Startled smiley. Socioeconomic and land use data. Population, number of households, income, car ownership, employment, and land use types, residential, commercial, etc., at the TAZ level. This data drives the trip generation step. O transportation network and service data. Detailed data on roads, geometry, capacity, public transport, routes, frequency, fares, travel costs, and key nodes, e.g., park and ride facilities. This is crucial for the mode choice and route assignment steps. Point 4. Future forecasting inputs. To forecast future travel, the model requires predictions of socioeconomic data, future population, households, employment by sector, and income levels per TAZ, land use plans, master plans, new large-scale developments of shopping malls, housing estates, industrial parks. Transportation system changes, new roads, expanded capacity, new public transit lines, changes in fares, and new traffic policies, e.g., one-way streets, congestion pricing. Government policies. Environmental regulations, carbon reduction targets, and car restriction measures. The four sequential steps. Step 1. Trip generation. This step estimates the total number of trips originating, trip production, and ending, trip attraction, in each TAZ. Methods, cross-classification, or regression analysis. Variable. Startled smiley. Independent, population, land use, income, car ownership, economic activity in the TAZ.O dependent. The number of trips. Trip purposes. Trips are categorized for accuracy, e.g., home-based work, HBW, home-based education, HBE, home-based shopping, HBS, home-based other, HBO, non-home-based, NHB. Output. A table of total trip productions, P tilde I tilde, and attractions, A tilde I tilde, for every TAZ. Example, regression model A HBW trip production model might be P underscore I equals minus 43.6 plus 0.097 asterisk population underscore I plus 0.773 asterisk. Employed residents underscore I plus 0.504 asterisk number of cars underscore I if a TAZ has 2,000 people and 1,000 cars. The estimated productions would be calculated accordingly. Step 2. Trip distribution. This step determines whether trips generated in Step 1 go. It creates a flow of trips between every pair of zones, resulting in an origin-destination, OD, matrix. Methods. Growth factor model or gravity model concept. Inspired by Newton's law, it states that the number of trips between two zones is directly proportional to their trip productions or attractions and inversely proportional to the friction, or impedance, e.g., travel time, cost, distance, between them. O formula, T underscore ij equals K asterisk, P underscore I asterisk A underscore J, F, C underscore ij. O where T underscore ij is trips from I to J, P underscore I is production in I, A underscore J is attraction in J, F, C underscore ij is the impedance function, e.g., travel time squared, and K is a balancing constant. Output. The OD matrix, or trip table, which shows the number of trips between every origin and destination zone. Step 3. Mode choice, modal split. This step estimates the proportion of trips between each OD pair that will use each available mode of transport, e.g., car, bus, train, bicycle. Methods. Diversion curves or, more commonly, discrete choice models like the logit model, data used, travel time and cost for each mode, traveler socioeconomic characteristics, age, income, car ownership, and trip purpose. Logit model calculates the probability of choosing a mode based on its utility, the measure of its attractiveness, often a linear function of time, cost, and other attributes. O binary logit, for two choices P, I, equals E caret, U underscore I, / E caret, U underscore I, plus E caret, U underscore J. O multinomial logit, MNL, for multiple choices P, I, equals E caret, U underscore I, sigma E caret, U underscore J, for all modes J. Output. OD matrices split by mode of transport, e.g., a car OD matrix, a bus OD matrix. Step 4. Route choice, trip assignment. This final step loads the mode-specific OD matrices onto the transportation network, assigning trips to actual routes. Method startled smiley. All or nothing. AON assigns all trips between an OD pair to the single shortest path, in terms of time or cost, under free-flow conditions, no congestion. It is simple, but unrealistic for congested networks. O user equilibrium, UE, incremental AON, more advanced methods that account for congestion. Trips are assigned in iterations, with travel times updated after each assignment based on volume delay functions, e.g., the BPR function, T underscore A equals T underscore A, caret 0 asterisk, 1 plus 0.15 asterisk, of V underscore A, a C underscore A, caret 4. This continues until no traveler can reduce their travel time by switching routes. Output. The final link volumes, number of vehicles or passengers on each network segment, travel times, and other performance metrics. Conclusions and key lessons applications. The model's outputs, link volumes, can be combined with capacity to determine the level of service loss, congestion delays, emissions, fuel consumption, and total travel costs. Critical step. Trip generation is the most crucial step, as errors here propagate through all subsequent steps. Accuracy drivers. The The model's forecasting accuracy depends entirely on 1. The quality and detail of the data used for calibration and validation. Point 2. The accuracy of the future input forecasts, population, economy, land use. Land use as step 0. Accurate land use modeling is critical for providing reliable future inputs. Known limitations. The 4-step model, especially its mode choice component, has a history of significant forecasting errors globally. A common issue is the overprojection of public transit ridership, sometimes by as much as 100%. In summary, while the 4-step model is a foundational and widely used tool in transportation planning, its practitioners must be aware of its limitations and ensure rigorous data collection and validation to produce meaningful results. Lecture 1, ASK, Introduction to Transportation Planning. Transportation planning process. 1. Presented as step-by-step, in reality complex and overlapping, cyclical. 2. Starts with identifying community problems, ends with designing solutions or projects. 3. Updating or validating existing plans, not start from zero. 4. Support decision-making. Major steps of transportation planning. 1. Context and problem identification. 2. Vision, goals and objectives. 3. Data collection, analysis and evaluation. 4. Plan development and programming. 5. Project development. 6. System monitoring and feedback. Changing context for transportation planning. 1. Population growth and urbanization. 2. Demographic shifts. 3. Economic transformation. 4. Infrastructure preservation and resilience. 5. Technological change. 6. Financial and institutional change. 7. Environmental pressures and energy transition. Key features of modern transportation planning. 1. Broader scope, visioning, implementing and monitoring. 2. Performance measures link planning to decision-making and feedback. 3. Multiple strategies, infrastructure, TDM, ITS, policy actions. 4. Applicable globally. 5. Continuous feedback. 6. Framework to assess planning effectiveness. Legal and institutional framework in transportation. 1. Define role of national, regional and local agencies. 2. Planning tied to funding, required to access to national and international funds. 3. Emphasis public participation, environmental review and coordination. 4. Promotes multimodal, performance-based planning approaches. 5. Ensure consistency, accountable and align with national goals. Chiang Mai Integrated Public Transport and Active Mobility Plan. Goals. 1. Increase public transport share by 25% by 2035. 2. Reduce PM 2.5 by 30%. 3. Accessibility for vulnerable groups. Plan. 1. Short. Pilot e-feeder bus, sidewalk or bike lane upgrades. 2. Medium. Expand network, integrate ticketing. 3. Long. Full multimodal smart mobility. Relationship between road classification and road function, arterials, collectors, local streets, mobility, land access, transit data collection and analysis. Methods. 1. Ride checks. 2. Point checks. 3. Automatic passenger counter. 4. Survey. Applications. 1. Service optimization. 2. Performance monitoring. 3. Marketing. 4. Fare policy, pedestrian studies, key metrics. 1. Volume, flow rate, density, walking speed. 2. Loss for pedestrian facilities. Parking studies. Study elements. 1. Parking inventory, on street and off street. 2. Occupancy, turnover, peak demand period. Applications. 1. Parking pricing. 2. Demand management strategies. 3. Land use planning improvement.